In the previous section, we talked about all the different nuclei that make up the basal ganglia and their rough locations relative to each other in the brain. Now, like the cortex and thalamus, these basal ganglia nuclei have projection neurons that project outside of the nuclei themselves. But there's a major difference between the basal ganglia and, say, the cortex, because in most of the basal ganglia nuclei, the projection neurons are in fact inhibitory. Their neurotransmitter is GABA, they're GABAergic projection neurons. And in fact this applies to the striatum, the globus pallidus, and the pars reticulata of the substantia nigra. However, the projection neurons in the pars compacta of the substantia nigra are in fact dopaminergic. The projection neurons in the subthalamic nucleus are actually excitatory. They're glutamatergic. Now, in addition, most of these structures also have inhibitory interneurons that are GABAergic, and a few have neurons with other types of neurotransmitters as well. So with all these differences, why do we think of the basal ganglia as a single anatomical structure? Well, the reason is that there's a pronounced pattern of connectivity amongst the different basal ganglia nuclei and with other structures. The primary pattern is that outputs from the cortex go to the basal ganglia. They are processed in the different basal ganglia subnuclei, and there's a return projection to the cortex via the thalamus. Within the basal ganglia, there's processing of cortical inputs and feedback loops modulating that processing. So let's have a look at this connectivity in more detail, focusing on the dorsal basal ganglia. There's massive excitatory input from the cortex into the striatum. Outputs from the striatum come from the GPI-SNR and target the thalamus. And as discussed earlier, there's a positive feedback loop between the thalamus and the cortex. The GPI-SNR neurons are inhibitive, and in their regular state they fire continuously, what's called tonic firing. This constant tonic inhibition puts a brake on the corticothalamic feedback loop. But if the brake is relaxed, if the inhibition by the GPI-SNR is reduced, then activity will build up in the cortex. Within the striatum, there are two populations of neurons, labeled D1 and D2, because one population has more D1 receptors for the dopamine neurotransmitter, and the other population has more D2 dopamine receptors. Both of these populations are made up of very similar inhibitory projection neurons. There's a direct pathway that links the D1 inhibitory neurons to neurons in the GPI-SNR. So if these D1 neurons fire, they'll inhibit the GPI-SNR neurons, which will reduce the tonic firing of those neurons and therefore reduce the inhibition of the thalamus. So activity in the D1 neuron population will tend to increase cortical activity. There's also what's called an indirect path between the D2 population and the GPI-SNR. This indirect path goes through the GPE and then the subthalamic nucleus. The projection from the subthalamic nucleus to the GPI-SNR is excitatory, and because of the detailed connectivity of the indirect path, an increase in the activity of the D2 population will increase the inhibition of the thalamus and reduce cortical activity. In this picture, the STN is only getting inhibitive inputs. However, the glutamatergic STN neurons also fire tonically, providing a base level of excitation to the GPI-SNR. In addition, the STN gets input from the cortex and the thalamus and projects back to the GPE. So the effect The overall effect is that the direct and indirect paths act in opposite directions on thalamic and therefore cortical activity. There's also a feedback loop from the GPI-SNR back to the striatum. This feedback loop acts via the dopaminergic neurons in the SNC, and the key factor is that an increase in background dopamine in the striatum increases the relative activity of D1 neurons to D2 neurons. This will increase direct path activity versus indirect path activity. So overall it will reduce GPI-SNR activity and increase thalamic and cortical activity. Once again, the picture is a bit more complex because there's also excitatory connectivity from the thalamus back to the striatum. And in fact, there are quite a few connection paths between different nuclei that I'll address a little bit more later in the course. But on the other hand, this simplification represents a good way to approach functional understanding. Massive inputs to the basal ganglia from the cortex that are processed through two parallel paths with a feedback loop regulating the relative activity in the two paths. Then outputs from this processing regulate the activity of the cortex. So the basal ganglia is somehow using the outputs from the cortex to influence cortical activity. Now, we noticed earlier in the course that in the cortex, neurons and higher structures don't correspond with specific behaviors. However, a clue to what the basal ganglia are doing can be found in the observations that neurons and small groups of neurons in both the striatum and the GPI-SNR do correspond with specific behaviors. So, part of the transformation of cortical information by the basal ganglia involves information about specific behaviors. And again, we'll return to this point later in the course.